Greetings, in this one we'll do something with a directed graph, also called digraph, which is a shortcut name for it, for the same thing. So it's a graph where edges don't have no direction and just connect to vertices, but it's a graph where each edge has its direction. So let's see an example of it. So the thing we'll be talking about, let's say, this is our example first of all. So this is the example. 3 vertices, ordered directed edges as follows. And I'm not going to go deep into digraphs or directed graphs because that's not the main point. We're doing a side note about it. And the side note is as follows. We know this interesting theorem from graphs in general, undirected, which says that if you add for some graph G with vertex set V and edge set E, if you add all the vertices degrees together, you will get double the magnitude of the edge set. So if we have a graph, let's say, like this, then each vertex has a degree of how many edges are connected to it. So these are the 3 vertices, these are the edges connecting them, and each vertex has how many edges connects to it, that's its degree. So it's 2 plus 2 plus 2 will be this value here. We add the degree of each. This vertex has 2 edges, so it has degree 2. This one also, this one also. So in total 6, and it should equal to the double of the amount of edges in that graph, which is true. It works. So for simple graphs or normal undirected graphs, we know this turns out to be right. And there's a generalization of it also for directed graphs. So let's see about that. First of all, with directed graphs, you might more often encounter that there's like, well, first of all, I'll name the nodes. Why not do that? So we can do that. And also I could name the edges with letters, for example. Then with directed graphs, maybe more often one is confronted with the fact that things are more marked, even the edges. Then we can say, oh, this edge, because edges have to be ordered pairs where the order matters, because C is an ordered pair 3, 2. It really specifies 3 to 2 is the edge, not 2 to 3, because of the arrow's direction. So with this graph now, we want to generalize that previous theorem, and it's going to be as follows. Basically, with this example, we'll look at how it turns out. Check it. But we can do a proof in a future one. We could do a proof in the future one, we'll see. So basically, let's write down that theorem. The theorem says that if you do again the same thing, now we have different degrees. That's basically our main point here. We have different degrees for the vertices. The degree is still the same idea, but we need a special degree for each vertex that specifies how many arrows go into it and how many another degree for how many arrows go out of it. So there's so-called in degree and a so-called out degree. So out degree will be degree plus, and in degree will be degree minus notation. So that's that. And the theorem then translates in terms of these two. So we will not have just 1 degree and that equals 2e, 2 times the magnitude of the edge set, 2 times the number of edges in that graph, but it will again be equal to 2 times the edges or 1 times the edge, depending on how we formulate it. But the way I will formulate it, it will equal to 2 times the magnitude of e again. So it's same on the right side. So it reminds us of that. And then on the left side, it will be in terms of the minus and plus the degrees. So first the minus degree, that means for each vertex how many arrows go into it of each vertex V. And then the sum, again, of all vertices of the vertex set for their degrees, about their degrees that how many arrows go out, how many edges have this vertex as their source, how many arrows go out of how many arrows / edges, the same thing meant in this case the whole time, go out of this vertex. And that will again equal to the double of the magnitude of E. So let's say this is our G, it has vertices V and edges E, but now edges are directed. They have to be ordered pairs, by the way, information. And let's now proceed to check it. So, well, we'll have 2 numbers, and we'll see. Well, the magnitude of E is already more clear than having to look for these. That's going to take longer. So let's just write the right side first though. So how many edges we have? Well, even here are 2, each in their own direction, but I will write them down. So 1, 2, 3, 4, I will count them. So we have 2 times for the right side, which will be 8. on the left side, let's see. So the degrees of each vertex, of how many edges go into that vertex. So let's start with 1. So into it goes nothing. Then 2, then 3, for example, let's go this way. Into it goes 1. Well, here that's not recognize it once again. 1 into it goes 1. Also, this A goes into it. Then for 3 into it goes again 1. And for 2 into it go 2. So in total 4. And let's see for each vertex how many go out of the vertex. So 1 out go 2. 3 out go 1 out go 2. 3 out go 2. A and C. And 2 out go 0. So again, it's true. So 4 plus 4. So yes, on the left side we have 8 as well. So it's right, we checked it. So for this example. So we see the idea here is though not to think that degree minus sum and degree plus sum are somehow different and then they turn out to be 2e also. Actually they're both equal to e. So one can just take the minus and plus and they're both equal to e. Even here we saw it 4, 4. In this case it was one example, but this doesn't have to prove everything, right? So to have a proof, that's a proof. We're not doing that now, but we saw here with an example that, and it's a random one, turns out as stated. So once again, the theorem talks about the relation between the degrees of all the vertices and the number of edges of that graph, but now we have to talk about degrees in terms of in degrees and out degrees.